Welcome, explorers, to our webinar on the role of plasmas in astrophysics, Astrophraya 24, organizing by Biomedical and Earth Science Division, SEDS OUSL. It's an absolute pleasure to have every one of you joining us today as we embark on a journey to the depth of space and time. So, I'm 𝗏𝗏𝗏𝗏, your moderator of today event, and 𝗏𝗏𝗏𝗵 will be joined as my fellow moderators soon. Don't miss out on these opportunities and gain actionable knowledge. Together, let's explore new ideas, share experiences, and elevate our learning to new heights. Stay tuned, stay engaged, and let's grow together.
Now the Assistant Manager of Biomedical and Earth Science Division, Mr. Dylan Rodrigo. I invite you to conduct the welcome speech.
Good evening, all of you. Welcome to our Astrophraya 2024. I am delighted to have you all here, including our guest speaker, Dr. 𝗤𝗏 and all participants from universities and schools. Astrophysics brings together science and curiosity, and today we gather to learn and inspire each other. A big thank you to the board of SEDS OUSL and the organizing committee of SED Sri Lanka for making this event possible. Dr. 𝗬𝗏, we look forward to your insight. To all participants, your passions, astrophysics is what drives this field forward. Engage, ask questions, and share your ideas. Remember, somewhere, something incredible is waiting to be known. Let us explore and discover together. Welcome again to Astrophraya 2024. Thank you.
Thank you, Dylan. And now I'm going to invite our guest speaker, Dr. 𝗤𝗏𝗏𝗏. He is currently a postdoctoral research fellow and lecturer in aerospace propulsion at ANU College of Engineering, Australia. His research focuses on exploration of advanced material of space propulsion, specifically targeting satellites and CubeSats. He holds a PhD in plasma physics and nanotechnology from Queensland University of Technology, Australia, a Master of Philosophy in Condensed Matter Physics from the University of Peradeniya, Sri Lanka, and a Bachelor of Science degree in Biological Sciences from the University of Rouen. Dr. 𝗏𝗏𝗏's outstanding contribution to his field have been recognized through numerous prestigious awards and grants, including the New Space Research Network Research Pilot Grant, Project Grant, ANU Research Pipeline Seed Funding, and the NRC Merit Award for Scientific Research. Sir, this is your moment to talk to us.
I think everyone can see me and hear me. Thank you very much, SEDS Organizing Committee, for having this wonderful Astrophraya 24 and also inviting me. And before I start, I would also like to thank especially for Professor 𝗤𝗏 𝗏𝗏𝗏. He's the one who actually being the initial contact for this event, and also he used to be my PhD, my MPhil supervisor during my time at NIFS Sri Lanka. My name is 𝗤𝗏, and I teach propulsion systems at ANU. So we have a aerospace major course in our engineering faculty. And also I'm doing some research on electric propulsion systems and advanced materials for spacecraft. Let's move into the first slide of today's seminar. Okay, so first of all, most of you have heard about cities of Melbourne and Sydney in Australia. So actually ANU located somewhere called Canberra. So Canberra is the capital of Australia, but many people never heard about such city. So so we have Melbourne here, Sydney here, and Canberra is located somewhere in between. It's a very small piece of land, but that's the capital. So this is how the city looks like. Can you see the slides? Can someone please let me know? Anyone from the organizing committee? Can you please?
Not yet, sir.
Oh, something went wrong, right? Hang on. Let me try to share it again.
No, okay, sir.
Now we can see, sir.
Okay, great. Okay, that's how technology works. Anyway, so now I'm just moved to the next slide and I hope you can see. Please correct if I'm wrong. You can see it, right?
Yes, sir.
Okay. All right. So if you are aware about the date of today it's 19th of July. So I'm not sure how many of you remember, but tomorrow marks the 55th anniversary of the moon landing. So importance about Canberra in terms of Apollo mission or the historic moon landing is this Parkes radio telescope, which is located very close to us. And this radio telescope is used to get the live transmission from moon during the Apollo missions and later missions as well. And another important landmark in Canberra is this NASA Deep Space Complex. So most of the major missions that is taken place at the outer solar systems, for an example, something like Voyager 2, the continuous transmission between these spacecrafts is taken place by this deep space complex. So there are three main antennas located throughout the globe. So there's one located in USA, another one in Spain, Madrid in Spain, and the other one located at Canberra. So, and out of these three antennas, the Canberra Deep Space Complex having the biggest antenna, something closer to 73 meters, I guess. And this is the only antenna capable of sending signals to Voyager 2 and Voyager 1 spacecraft. The other two can actually receive these signals, but for transmission, this Canberra complex is being used. And this is just one example. And for the other missions that Canberra Deep Space Complex is responsible include some Mars missions, sending commands to NASA rovers, and also I'm not sure you are familiar. There's another satellite called SOHO, and lunar reconnaissance orbiter. Those are the examples that I can think of at the moment. So there are several special infrastructure and locations are located close to Canberra in terms of space exploration. So let me briefly explain about Australian National University as well. So this is where I work, School of Engineering. So we are mainly working on space technology development, to be honest. But today I know most of the audience is interested on astrophysics. So for you, we have a School of Astronomy, which is part of our School of Science. So in Canberra, we have really good night skies, unpolluted from light. So it's it's a very common sight that we can see Milky Way in our naked eyes. And we have a complex of telescopes. We call that Mount Stromlo Observatory. So we have number of observatories like these, which are conducting research on astrophysics and cosmology. So yeah, if you are interested on pursuing your master's or PhD in astronomy or cosmology, I highly encourage you to apply to NU. And I later in this lecture, I put another separate slide specifically about this application process as well. So stay with me. I will explain more about that later. Another thing about ANU is, so this guy over there. So this is our former Vice Chancellor of ANU. He's Professor Brian Schmidt. So he won a Nobel Prize in 2011. So he's the one who actually discovered the accelerated expansion of the universe. So you might be aware that the expansion of universe. So before Professor Brian's discovery, people believed that the universe, the expansion of the universe is slowing down. So after the Big Bang, the universe started to expand, and people believe due to the gravitational effect, it is slowing down. But Professor Schmidt, he was looking for evidence about the slowing down of the universe by using a type of supernova called type 1a. But according to what he discovered is something contradictory with the theories that was built during those days. So according to him, the universe is not slowing down. Instead of that, it is accelerating. So this gave birth to the idea of dark energy. The concept of dark energy is established after his discovery. And so he started these experiments in late parts of 90s. And after so many observations and experimental results, he was finally awarded physics Nobel Prize in 2011. So, and now he's no longer working as Vice Chancellor, but he's still doing his research in fields of astrophysics actually in this Mount Stromlo Observatory. So another reason for you to study in NU if you're interested. All right. So today's topic, the role of plasmas in astrophysics. So before we discuss further about this topic, let me ask you a question. What is plasma? So I can't put a poll and get your answers, but think what your answer is. I will give you, let's say, 5 seconds to think about, and afterward, I'll proceed. So what is plasma? So when that word comes into mind, some of you might be thinking about this, plasma TVs. And I know there are some students who, especially the students who studied biology for their A-level, so who remember biology from their O-level science, they might be thinking about this. So yeah, plasma TV is one thing. We get the term plasma. And another thing is blood plasma, where the various blood cells are suspended. But in physics, we have a different meaning for plasma. Actually, in physics, it's a state of matter. So then the question comes into our mind is, what is matter? So basically, matter is anything that has mass and takes some space. So if you think deeper into matter or about the basic units or basic building blocks of matter, it is called atoms. So there are some matter made entirely of one type of atoms. We call them elements. And there are things that made of combinations of atoms. Yeah. So, so is there anything else other than matter in this universe? So anything that are not made of atoms? So what are those things? Actually, there are some things like that. For an example, heat. There's no matter. So we can, it's not made of atoms. So it's not matter, non-matter. Light. And things like emotions, thoughts, ideas. So these are non-matter things. So that's the main difference between matter and non-matter. And if we learn more about how this matter is made, we can see there are three main types of matter in our environment. But when we go to universe, actually this changes. But mainly in our surroundings, we can see solids, liquids, and gases. So this is something we learn in, I think, grade 8 or 9 science classes. So in these three states of matter, the properties of these states are actually depending on the bonds between the principal building blocks. So what are these principal building blocks? Those are atoms. So if we consider a solid, so there are more rigid bonds in between these atoms or the building blocks or these small particles the matter is made of. So because these bonds are rigid and strong, we can see a definite shape and definite volume in solids. And also because these particles are packed together, they have high density. And solids can be compressed very little, but we can say it's almost, or it is a bit tricky to compress, but it is compressible. So when it comes to liquid, the bonds are much more, those are not rigid as it used to be in solids, but still there are some bonds. And in liquids, there is a definite or specific volume, but when it comes to shape, it is taking the shape that we put, it is taking the shape of the container that we are going to put the liquid. When it comes to the density, it is less dense than solid, but it is having more density than a gas. And liquids are slightly compressible compared to solid. When it comes to gas, there's no shape, no volume. There's no definite shape, no definite volume. When it comes to density, it's comparatively less, and it is highly compressible. So what makes this difference between all these states of matter? So for an example, if we take ice as a solid, if we provide some heat or if we provide some energy into ice, it converts itself into water. And if we continuously providing energy, then it forms water vapor, or it converts itself into gas phase. So by providing energy, we can change the bond strength, and based on that, the physical properties are going to change. So what happens in plasma phase? So plasma phase is something lying beyond the gas phase. So if we continuously providing energy into a gas, the internal structure, the internal particles or the atoms are going to change into the subatomic particles, which forms, which is not seeing inside gas phase. So let's take a look at how the atomic structure is and how that atomic structure is going to change when we are providing energy into this gas phase. Okay, so in our standard textbooks, if you have a look at how atoms or substances are formed, you can see this kind of image. So you can see a lattice structure. Okay, I don't know how this works, but someone is moving my mouse. Okay, now it stopped. I don't know how it. Okay, it's weird. Anyway, I wanted to stop in this specific picture. So this is how atomic structure looks like in a standard science textbook. So if we have something to magnify any standard matter, we should be able to see a picture like this. So again, I don't know what's happening. Anyway, so what we need to do is an instrument which can magnify standard matter. So in other words, a microscope. So in our schools, we have light microscope, but the magnification of a light microscope is something in 1,000 times of magnification. So we need something better than that. So we have electron microscope. So there's a type of electron microscope called TEM, transmission electron microscope. So usually in a standard TEM, you can go up to a magnification of 2.3 million of magnification. But if you have a magnification more than 2.5, actually you can see atoms. So this is such image taken by a special type of TEM. So this microscope is called 𝗔𝘀ᴏᴜ atomic resolution microscope. And this substance, this one is called molybdenum disulfide or MOS2. So this is how we see MOS2 in standard form, and this is how it exactly looks like when we look at through the microscope. So okay, something wrong with my mouse, but ignore that. So each of these bright colored dot represent an atom. So you can't see the bonds between them, but you can still see the 2D structure of this material. So if you magnify it further, or the standard model of the atom, it looks like this. So we have a center part, we call this nucleus. So in nucleus, we have several subatomic particles. There are some charged particles, we call them protons, and there are some neutral particles, we call them neutrons. And around the atom, we have negatively charged particle called as electron. So this is how the standard model of atom looks like. So what happens during the phase change between the gas to plasma is we are providing sufficient energy to get these electrons out of the atom. So in a gas phase, we have neutral atoms, but if we provide sufficient energy, we call this ionization. You might remember that learning first ionization energy, second ionization energy, things like that. So if you provide energy more than the minimum required energy to jump an electron out of the nucleus, we call this that ionization energy. And once you have this ionization energy, instead of gas, you have a mixture of these positively charged center parts or nucleuses and negatively charged electrons in one medium. So this medium we call as plasma. So plasmas have completely different physical properties comparing to gas. Actually, there are some properties which are similar to gases. For example, plasmas and gases both can be compressed, and they have low densities, but actually it changes. For an example, if we consider a plasma in sun or in steel atmospheres, those are called high density plasmas. So the density can go high, but still most of the time we can say still gases and plasmas having almost similar density properties. But there are some properties which are entirely different from gases. For an example, electrical conductivity. In normal states, gases are actually, they do not conduct electricity at all. But plasmas can conduct electricity very well. And also plasmas, if you put a magnetic field, plasmas are responding to magnetic field, but gases doesn't show that property as well. So there are some similarities between plasmas and gases, and also there are some big differences as well. So if we summarize what we already learned during these slides, so we have 4 phases of matter, liquid, solid, and gas in our regular temperatures and pressures. But if we provide additional energy into gas phase, we can get another state of matter called plasma. So let's have a look at the history of plasma. So when we look at the history, there's this guy called William Crookes. So William Crookes is the one who invented the cathode ray tube. And also he did some work in spectroscopy, vacuum tube technology, and flame spectroscopic techniques. So he's the one actually discovered plasma as a separate state of matter. But he named it as a radiant matter because in his cathode tube, you can see the plasma is actually glowing inside this cathode tube. So next, we have J.J. Thomson. J.J. Thomson is the person who discovered electron. So, and also he's the one who came up with a plum pudding model of the plasma, of the atom. So he's the one who proposed that plasma is actually a soup of electrons and positively charged nucleus. So then we have the most important person in plasma physics, maybe father of plasma, Erwin Langmuir. So he's the one initially used the term plasma because actually he also studied some biology. So he felt that this is something similar to the blood plasma, because in blood plasma, it's a liquid that suspends other blood cells like red blood cell, white blood cells, etc. So Langmuir has seen that plasma is a medium that holds these positively charged ions and negatively charged electrons. So he named it as plasma, inspired by blood plasma. So that's a short history of plasma. So in our day-to-day life, okay, again my mouse is playing, so please ignore that. In our day-to-day life, we are mainly seeing solids, liquids, and gas phases, but there are some plasmas also. Again, in plasma TVs, yes, we have plasma. and lightning. So I think most of you are aware about how lightning works. So we have either positively or negatively charged cloud, and comparing to that, the Earth is acting as a ground. So when the potential between these gas clouds and Earth exceed some limit, it is going to ionize the atmosphere, and there's a big discharge taken place. So this is called the lightning. So lightning is actually um, for a really short time, it is ionizing air, and it is creating a plasma channel between the clouds and the ground. So that's one example that you can see plasmas in day-to-day life. Another example is fluorescent tubes. So now we have CFLs, and some households still use fluorescent tubes as well. So inside the fluorescent tube, actually, you have plasma. So you have low pressure mercury gas inside that. So it is producing the UV light, and there's a phosphor coating inside this glass tube, and it creates this white light. In arc welding, we are using plasma, the heat of plasma, to melt two metals together and weld. So for in plasma and in arc welding, we are using this kind of oxyacetylene or oxyhydrogen flame tape. I don't know this road signs still located in Kandy, but when we are young, we can see them in Colombo Street. So these are neon signs. So inside these neon lights, it's actually plasma. So we energize neon gas and creating these kind of beautiful lights. Another example is these kind of testers. So inside the tester, we have a neon light. So similar to those, this is actually a low pressure plasmas. So these are some examples that we can see plasmas in our day-to-day life. So when it comes to cosmology, there are more examples. So in a known universe, I think, okay, I don't remember the exact numbers, but I think majority belongs to dark matter, and remaining the non-matter is a very small proportion, and out of that small proportion of non-matter, mainly, I think more than 99% of this non-matter is in the form of plasmas. So if you look at the sky in daytime, you can see sun, and sun is actually a big ball of hot plasma. And if you have a look at the night sky, you can see so many stars, and actually these stars are made of plasmas. And in between these stars, again, it's interstellar gases, but actually interstellar gases is in the form of plasma. So these these interstellar gases, or these nebulas, are actually made of plasma. And another example is comet tails. These are also made of plasmas, and the list still goes on. You can see auroras not only on planet Earth, but on other planets as well. So these auroras are also made of plasma. So how this aurora phenomenon take place? So when the solar wind is having a collision, so solar wind is mainly composed of charged particles coming out of sun. So mainly these particles are originated in magnetosphere, and when they interact with Earth's upper atmosphere, it creates plasma. If we have a look at the sun's atmosphere or sun's plasma, so solar plasma, the temperature is really high. It's something closer to 15 million degrees in Celsius. And because of this extreme heat, we can see a fusion reaction, or nuclear reaction between hydrogen nuclei, and they are producing helium atoms. So this is producing a really big amount of energy, which powers the life on Earth as well. So, but if you have a look at the sun's plasma, you can see it's not uniform. So it's structured into several layers. So the innermost core, that's where the nuclear fusion is taking place. And surrounding that, this is called, the area is called a radiative zone. So that's where the energy gradually diffuse outwards. And beyond this layer, there's another zone called convective zone. So in here, the plasma is a little bit different. So it's called a turbulent plasma. So this turbulent plasma transport energy from sun's surface. And the outermost layer is called a photosphere. So that's what we can see visibly as the sun's surface. And just above this, there's another layer called corona, so sun's outer atmosphere. During solar eclipse, you can see this corona. So this solar corona, this extend millions of kilometers away from the sun's surface. Yeah, so that's how the behavior of sun's atmosphere or sun's plasma looks like. So by looking at the suns, we can assume that other stars are also similar to that, but the sizes of these stars, they are vary in size. Temperatures are also varying, and also the luminosity. Similar to our sun, nuclear fusion is taking place inside these stars. So they convert hydrogen into helium. So life cycle of a star. So it shows the dynamic nature of the plasma as well. So stars beginning their lives as nebulas, was clouds of gas and dust, and then because of the gravitational force, they collapse, heating the material inside until the nuclear fusion ignites and giving birth to a new star. And during the age of the star, the plasma also undergo through various transformation. In bigger stars, fusion progresses beyond helium, so it also creates other heavier elements too, like carbon, oxygen, iron. And these stars may end their lives as supernova explosions. And then this cycle again repeats after these supernovas. They convert itself into gas clouds and then forming stars again. So this is an animation of how solar wind is affecting the Earth's magnetosphere, and the reaction or the interaction taken place between solar wind and the Earth's magnetic field. So because of these charged particles and the interaction between the Earth's magnetic field, it creates another phenomenon called auroras. So if we consider the particle energy of suns, usually they lies in 1 kilo electron volt range. In broader context, plasma helps to find out this stellar evolution and life cycle, and also how this kind of phenomenon taking place. So most of you have heard about auroras in northern part or in Arctic region of Earth. So these are called aurora borealis. And actually in our region, or the southern hemisphere region, we can also see aurora. This is called aurora australis. So if you were looking at the news in last couple of months, now we are at a solar maximum period. So we have more auroras taking place in our polar regions. So actually, uh, so this is a solar cycle taken place in every 11 years, and we are kind of at a peak. So we can see auroras more frequently in both northern and southern hemisphere. So as I mentioned earlier, so auroras taken place due to the collision of charged particles like electrons with the magnetosphere. So these charged particles, if we consider the energy levels, this could be between 1 to 15,000 electron volts, and they collide with the gases in the upper atmosphere of Earth. So, so these particles are sufficient to excite the atoms in these specific gases, and based on the gas type, we can see special types of fluorescence. For an example, oxygen, it gives this greenish glow, such as here. So, and also if you have oxygen in lower levels of atmosphere, it gives this kind of reddish glow. And the other colors, usually these purplish colors, these are originated due to nitrogen. So depending on the gas type, we can see specific types of light. And in Earth, we can see auroras in visible range, but in other planets, such as in Mars, we can see auroras in other portions of the electromagnetic spectrum. For an example, in Mars, the aurora light is more into the UV part or ultraviolet region of the spectrum. So you can't see them with the naked eye, but if you are looking through a UV camera, you can see them. So Earth is not the only place you can see auroras. There are auroras taken place in Jupiter and Saturn. The reason is both of these planets, they have their own magnetic field, much more stronger than ours. So we can see auroras in these planets as well. And before we move into the plasma located in interstellar space and the nebulas, I wanted to briefly brief you about dusty plasmas. So this type of plasma is called a complex plasma. The reason why it's called dusty plasma is in previously I told that plasma is mainly composed of charged atoms or charged ions and electrons. In dusty plasma, you have bigger particles as well, which are charged. So usually the sizes of these particles can be vary from 10 nanometers to 100 nanometers. So comparing to the size of the ions, so those are lying in picometer range. So comparing to that, we have more bigger particles in nanometer range in these dusty plasma. So dusty plasmas, we can see the examples I can give you is one thing is comet tails, the other thing is planetary rings. So those are the regions that we can see this type of dusty plasma. And also you can identify dusty plasma in interplanetary space as well. So yeah, so this is another special type of plasma that we can see in the universe. So in plasma clouds, so more commonly known as nebula. So these are massive regions of gas and dust scattered through our galaxies. So these clouds, they are mainly composed of hydrogen. So hydrogen is the most abundant element in the universe. So we can also see other traces of other elements as well, such as helium and heavy elements. So when these clouds reach critical mass, gravitational forces cause them to collapse and initiating the birth of new star. So this is one such example. So this is Orion Nebula. So this is located about 1,300 light years from Earth. So within Orion Nebula, we can see dense regions of plasma that are undergoing gravitational collapse, and that collapse is leading to formation of pre-star or protostar, and these protostars slowly, gradually accumulate mass, and when the cores heat up, they eventually triggering the nuclear fusion reaction and igniting themselves as new stars. And so this plasma in interstellar space, this is not static. It constantly influenced with various astrophysical processes. For an example, we have stellar winds from massive stars and shock waves from supernova explosions. So they inject energy into this interstellar plasma. So that create turbulent and dynamic environment. So these interactions can compress and heat the plasma, and that influence the formation of new stars. So also this interstellar plasma plays a major role in propagation of cosmic rays or high energy particles that travels through space. So cosmic rays, they can move through galaxy, they can interact with interstellar plasma, and also it can alter its path and energies. So studying these interactions, they provide valuable insight into the nature of cosmic rays and interstellar medium. And if we move further away in larger scale, so these kind of plasma clouds and interstellar plasma, these are integral compounds of cosmic wave, and we can see vast networks of filaments and voids that fills up, that makes large scale structures of the universe. So these filaments, some believe that these composed of dark matter, but according to what we can observe, this is composed of plasma as well. So these are kind of scaffolding structure that goes in between the galaxies. Yeah, so I will move into some experiments that we are taking inside our labs. So you might be thinking that making plasma is a complex process, but actually by using a very simple setup, we can create plasmas in our labs as well. So this is such setup. So this type is called DBD plasma, or dielectric barrier discharge plasma. So this is how the setup looks like. So we have two electrodes. So these are two metal electrodes. So in between, we have two quartz plates. So so this is more like a capacitor or a condenser. So in between, we have a gas channel. So usually we are using inert gases because inert gases are the easiest ones for us to make plasmas or ignite plasmas. And we can in order to energize these gas, we can use a power supply, and to get more data about the current and voltage and the frequency, those kind of things, we can use oscilloscope to get. And also to observe how the spectrum look like, we can use a spectrometer. So this kind of so this type of spectrometer, we call them as OES, or optical emission spectrometer, because all the plasmas, they emit light. So if we can observe this light and if we can resolve it through a prism, we can get the spectrum out of it. So to get that purpose done, we are using a spectrometer. And yeah, this is how this plasma setup looks like. And this is a magnified photo of how the setup is made. So if I elaborate more about the power we are going to use, in this setup, we are using AC current. So the frequency is somewhere around 400, 500 kilohertz. And yeah, by using this kind of setup, we can ignite a plasma. So I'll show you how it looks like in this video. So so this is the gas tube that we are injecting the plasma carrier gas. So in this case, it is argon gas. And so this is the quartz plate. And inside, you can see this blue glow of the plasma. And these are the two metal plates. So you can't see the power supply properly here, but the working electrode or the positive electrode is, given into this top electrode and this bottom electrode, and all this all this plate is grounded. So that's how the connection is made in this setup. So that's how the DBD or dielectric barrier discharge can be used to generate plasma. And there's another setup called plasma jets. So in here, we have two electrodes, one high voltage electrode at the center and ground electrode at the surrounding wall. And similar to the previous case, if we provide an AC power into this setup, and if we pass a gas through this nozzle, we can get a plasma. And similar to previous case, we need to have a power supply to ignite the gas. And also we need to have a gas pump to feed a gas through this plasma jet. And also we have a spectrometer to analyze how the spectrum looks like. So this is an actual setup. So this is the plasma nozzle, and this bright orange tube is the gas feeder tube, and you can't see the power line actually, but I'll play this video. This is how it looks like. So this, I'm not sure you can see it properly, but this is the plasma plum or the plasma flame. And another important thing about this jet is it looks like a plasma flame or something really hot. But if you look at the if you look at it through an infrared camera, you can see the actual temperature is closer to the room temperature. So most of us having an impression that the plasma is something which can be, plasma is something that we can generate in really high pressures and high temperatures, but it is possible to generate plasmas in room temperature as well. And we have some other plasma setups that we can actually touch and nothing will happen. So yeah, so other than these high temperature and high pressure plasmas, we have this type of room temperature plasmas as well. And I'm not going to discuss about plasma characteristics, but I'm going to discuss one method that is more important when it comes to astrophysical observations. This is called OES, or the optical emission spectrometry that I discussed earlier. So this is how a OES setup looks like. So in here we have the plasma source, and the light or the emission produced from this plasma is passing through a lens and then sending through an optic fiber. So this optic fiber is connected to a optical emission spectrometer where we can resolve the lines. So these are two such spectrums that we taken. So this is actually a sodium salt. This is called PTSS sodium salt. So you can see really intense sodium line here and some oxygen peaks as well. And this is the OEX spectrum taken on atmospheric air plasma. So that's why you can see our air is mainly composed of nitrogen and oxygen. I think my numbers could be wrong, but I think it's something like 75% nitrogen and 21 something oxygen. So we have oxygen and nitrogen peaks here. And also in our atmosphere, we have water vapor. So water vapor we can see as OH peak. And also you can see H-alpha peak here. So you might be wondering why so H-alpha, this is responsible for hydrogen. So you might be wondering where on earth we have hydrogen in our air plasma. So this hydrogen is actually a byproduct of dissociation of water vapor. So the plasma energy is so high that it dissociates water vapor into hydrogen and hydroxyl. So that's why we have this H-alpha line over here and hydroxyl line over there. So how this characterization helps us on astrophysics. Okay, before move into that, I will show one more OES spectrum. So in this one, this is a OES of argon plasma. So if you remember in previous slide in DBD plasma, the plasma carrier gas or the plasma generation gas is argon. So if we get the spectrum of argon plasma through our OES spectrometer, we are getting this kind of specific lines which represent certain certain electron transitions of argon. So in order to resolve this line, or in order to identify this line, we are using certain databases. Most common one is called NIST database. So this table of data is taken from NIST database, and you can see each of these lines are represented here, and in here you can see the transition. So if you remember some of your A-level chemistry, you may remember that we have orbitals in our atoms like sp,d, etc. So you can see how the electron transition taken place and what are the respective wavelengths for each of these transitions by looking at this table. And these are publicly available data. So if you have this spectrum, you can easily identify what transitions are responsible for such emissions. So with that in my mind, in your mind, I will move into two more examples, which are quite interesting. So this one, so this is an interesting finding. So this is a water cloud located 140 trillion, located about 12 billion light years away. And interesting thing is this cloud holds more water than the entire oceans on our Earth combined. The exact number is 140 trillion times. So, so this is revolving around a quasar or a supermassive black hole, and it is consisting more water than ever we can imagine on our Earth. And I will show one more example. This is also something really interesting. So this is a gas cloud located about 10,000 light years away from us. Interesting thing about these gas clouds are by analyzing the spectroscopic evidence, this is mainly composed of alcohol. So this gas cloud is located in Aquila constellation, and this is nearly 1,000 times bigger than our own solar system. And this cloud holds 400 quintillion liters of alcohol. So the bad news is, one, it is located too far away from us. And the other thing is, it is mainly methanol. So you might heard about the disaster that taken place a couple of weeks ago in the sea. Few fishermen found a bottle, something similar to alcohol, but it is not alcohol. So same thing might be happen in here as well. This cloud is mainly composed of methanol, and also there are some other harmful chemicals as well, such as carbon monoxide and methane and some ammonia. So, but still, these are really interesting and fascinating discoveries we can make when we are doing cosmological observations through spectroscopic methods. So with that in my mind, I would like to conclude today's lecture. But before I finish, I would like to remind that most of the students here, I think you are maybe finishing your schools and doing your studies in your university or doing your undergrad studies. So if you have any plan to do your higher studies in ANU, I highly encourage you to go through this link. I can actually send it through the chat as well. So this is where all our higher degree by research or HTR research projects are published. So if you are interested on doing an MPhil, MSc or PhD, I would like you to go through this webpage and have a look. So you might find an opportunity. But I'm not going to discourage, but ANU is somewhat competitive university because we are 30th best university in the world. So it might be competitive, but still give a try because we never know. And also I would like to show you some of the facilities that we have in our advanced instrumentation lab. So this is where I'm doing most of my work. So this instrument is called Wombat XL. So this is a space simulator. So it can simulate orbital conditions. So let's assume that you are sending a satellite into space, and so sending a satellite into space is really costly, and you don't want to fail your satellite once you reach there. So in this one, we can actually test from CubeSats to 1.5 tons weighing big satellites. So it's actually a big vacuum chamber. You put your satellite in, you close the chamber, and then you can study how it behaves in space vacuum. Not just vacuum, it can simulate the radiation environment on a space as well. So something like what will happen if you expose into UV, the thermal cycling in low Earth orbit, those kind of thing. So we have those facilities, and this is the largest facility available in Southern Hemisphere. And also we have more satellite testing facilities. So this is such example. Actually, these are some of our students doing an experiment with vibrational testing. So this is actually a big speaker-like thing. So, you know, we have different types of launching vehicles. We have, for an example, SpaceX have their Falcon rockets, Russia have Soyuz rockets, etc. So each of these launching vehicles have a different type of acoustic profile. So this setup, we can feed this acoustic setup into this system, and then we can check how our satellites behaving, or how, whether is it possible for our satellites to sustain the launching sequence or the launching from Earth to the low Earth orbit or the desired orbit. So we can check whether it can sustain this high pressure and highly vibrational environment of these launching vehicles. So that's another facility that we have here. And also we are conducting some experiments with advanced composites as well. So these are called Captain. So if you are looking at a spacecraft, you can see it is kind of wrapped in this kind of gold foil-like thing. So this is a polymer called Captain or polyimide. So we are synthesizing different types of polyimide. We are modifying it and we are trying to make them more space durable. So these are some of the experiments that we are doing. So I think some of you might be interested in these experiments. So if you like, I just go through the available projects and apply. And I would also like to mention the university that I did my PhD. And yeah, the link is given here, so I can pop this into the chat as well. Important thing about 𝗬𝗂 or Queensland University of Technology is they are not thoroughly looking at your academic profile. If you apply to ANU, it's a requirement that you have a 4-year degree with a class and some interesting research profile. But in 𝗬𝗂, it's not a big deal, but so it's relatively easy for you to compete comparing to ANU. So just have a look at this website as well if you are planning to study after finishing your undergraduate program. So have these links in maybe the easiest thing is I'll put this into the chat and you can have a look. And these are just 2 examples. We in Australia there are various other universities as well, and in entire world there are a lot. So based on your academic plans, make the right choice. So yeah, and also I'm happy to assist if you need any further help. So thank you very much. Shoot me an email if you need any further help. And yeah, once again, thank you very much for SEDS OUSL team for having me here. And if you have any questions, it's time for you to ask. Thank you very much.
Thank you, sir, for your enlightenment presentation. I think we had brief and clear idea about the word of plasma and the surrounding of plasma. Now it's time for the Q&A session. Now you can submit any question you have regarding webinar. Please drop your question in the chat box. So I think we already have some question in our chat box. Can we move on?
Yeah. Like a membrane structure to barrier for internal-external exchange. I'm not sure, is this a question or not, the first one. Can you please send it again? I'm a little bit confused about that. Okay, there's another one called, it's a state of matter where matter is in hot ionic state. Okay, maybe I'm reading the wrong one. How can we get recording of this meeting? I think it's something the organizing committee can do. How do magnetic fields interact with plasma in astrophysical phenomena such as solar flares? Okay, this is a tricky one. I'll tell you why. So in plasma, there are we do have magnetic forces, and also we have electric fields working on. So actually in plasmas, you can see a wave-like phenomenon. And those are called Langmuir waves. So what happens is if you have, so let's say we have equally distributed positive ions and negative electrons inside the plasma. And hypothetically, let's assume you have moved these negatively charged electrons into one side of a plasma. So all of a sudden, we have negatively charged region and a positively charged region. But what usually happens is, due to these electrostatic forces, the negative attracts positive. So like a wave, the negatives kind of going into the other side of the plasma. But electrons are, if we consider the size of the electrons comparing to the ions, they are really small. So those are not going to stop. So what happened is we can see a wave-like behavior. So on top of that, we have magnetic fields as well. So if we consider the forces between this electrostatic force and magnetic forces, it is going to form a really complex behavior. So that's why if you are familiar with simulation, you can see for gas simulation, we have so many softwares and programs, and even mathematically, we can very easily simulate what's going to happen, because pretty much in a gas, by using Newtonian laws, you can predict what is going to happen. But in plasmas, that's not the case, because we have to consider both electric and magnetic phenomena. So it's really tricky, and that's why you don't see, actually, there's very few softwares you can see to simulate plasmas, because even with very high computing power, even with a supercomputer, it's tricky to simulate how plasma works. And that's one of the main reason why we can't make fusion reactions on Earth. I mean, we are somewhat there, but not totally, because of this highly complex nature comes with these magnetic fields and electric fields. So I'm not sure you use COMSOL during your undergrad programs. So COMSOL is a simulation program that you can very easily use in gas timings. But when it comes to plasma, it's tricky. So even the best plasma softwares we have, they are really expensive, and but they still have big limitations. They can't simulate every type of plasma because of this complexity of these magnetic and electric field. One way we can do is we can simulate plasma considering as single ions or single atoms. Those are called 1D plasma simulations. Those are the easiest, and those are the least ones that taking low computational power. But when it comes to 3-dimensional plasmas, that's hectic. The reason is there are so many variables and there are so many factors that we need to put when we are putting these magnetic and electric roles together. So yeah, it's a really tricky question and complex question that we are trying to solve. So I'll move to the next question.
So next question from Ravindu Senairatna. He asked from how does plasma contribute to the behavior and structure of the solar wind?
So if you take solar wind, the solar wind itself is actually type of plasma, because the solar wind, we can say that we are living inside the atmosphere of sun. The sun's atmosphere kind of going beyond the orbit of Pluto. We call it heliopause. So it's not a atmosphere comparing to the one we have on Earth, but in the outer space, actually it's charged particles and charged ions and electromagnetic radiation also. So we can consider this as a really low density plasma. So it's not plasma contribution, but it's like the structure itself is made of plasma. I'll go to the next question. How do the plasmas affect the polarization of light in various astrophysical settings? And what can this tell us about magnetic field structures? It's quite complicated. Yes. When it comes to the magnetic fields, that is a bit trickier. But in Australia, now we are actually building such facility to predict how this plasma and magnetic fields are interacting. It's called square kilometer array, SQA, I suppose. So yeah, once we have that set up, we would be able to answer that question. But so far, we only have some hypothesis. But when we have this square kilometer array is up and running, we should able to get more answers to that question. What are the implications of plasma effects on the propagation of electromagnetic signals from pulsars and I think magnetars? How can this be used to probe interstellar medium? So implications. So I'm not the best expert to answer that question because my research area is mainly on how to analyze plasma based on light. So fortunately for light, we don't have big impact from these magnetic signals or magnetic interferences from pulses. But we can give, by looking at this optical emission spectrometry, we can get a clear idea about the chemical composition of these structures. I'll move into the next one.
Yes.
Yeah.
From Shehan Manoj. He asked from previous question, and also how do plasmas in the early universe contribute to the formation of the cosmic microwave background?
So again, so cosmic background radiation comes from as a effect of the Big Bang itself. So again, so it's not about plasma's contribution, but the background radiation is a direct result of the plasma distribution of the universe itself. So it's like the universe is more than 99.9% is made of plasma. So it's not like contribution, it's like the result of the plasma in the early universe. What are the mechanisms behind the plasma heating in solar corona, and how does this relate to solar wind? Plasma heating. So plasma heating, this is a plasma heating can be conducted in various different ways. So in our lab setting, we have different types of way to energize plasma. So we are using a radio frequency. We use microwave. We can use AC frequencies. So actually, we can use DC too. It's called pulse DC plasma. But when it comes to sun, it's mainly because of the nuclear fusion process. Dr. Janit Gunazeg. Oh, thank you, Janit. Thank you.
I think so all of it's a final question in our chat box.
Final. Yeah, I think that's all right. Yeah. So yeah, once again, so I'm not the best astrophysics guy you can have, but so my work is more involved in how plasmas can be worked to modify surface and how plasma thrusters working in the low Earth orbit. So I'm more like a person in plasmas comparing to astrophysics. So my knowledge in astrophysics is somewhat limited, but I think I can still make the link between the astrophysics and plasmas. So yeah, if you have any further questions, yeah, feel free to send me an email or you can even contact me through the organizing committee. Other than that, I think those links, I think I should send it through the chat as well. I will do it right now. So if you are applying, that might be help. So this is the link for QUT. Did it send? I think my
No, sir.
chat is disabled or something. What happened here? Hang on, I'll try again. Okay, I got it. Everyone in this meeting. Okay, it worked. And yeah, this is the link for 𝗪ᴑᴇ if you are looking for a higher study opportunity at Queensland University of Technology. I recommend this place because this is where I did my PhD. And also there are lots of plasma research going on. And also this is not the best place for astrophysics, I would say, but astronomy related engineering disciplines, it's a good place. And also I will share the ANU link. So again, so this is the link for our faculty. So ANU School of Engineering. Other than that, if you're interested in astrophysics, we have School of Science, and they have so many programs, and they have the best people in the world who did some groundbreaking discoveries, such as Professor Brian Schmidt. So you can search that site as well and give a try in School of Science. But in School of Engineering, what we are mainly doing is actually technological improvements, and our work is more into space technology instead of astronomy. So yeah, depending on what you like, feel free to apply. And these are not the only examples. There are various universities in Australia, such as Monash, UNSW. UNSW have a really good ground station because I think they have 3 or 4 CubeSats owned by them. So yeah, there are so many opportunities that you can try. So do not even limit to Australia, around the globe. So just upgrade your skills, apply, and yeah, I'm wishing you all the best.
Thank you, sir. We move on our Q&A session end. Before the Q&A session, I want to mention one thing. We have dropped the feedback form into the chat box. Please feel free to share all your comments and suggestions here. Thank you very much, sir, for joining our webinar. We deeply appreciate your insightful contribution and the valuable time for share with us. So kindly accept our token of appreciation. As we near the end of our webinar, it's time to express our heartful gratitude to all those who made this event possible. I invite the Division Manager of Biomedical and Earth Science, SEDS OUSL, Ms. Nipuni Hera, to dedicate the thank you speech.
Good evening, all. Thank you so much for all joining us today. We are having 90 plus participants today, so I'm very glad. And we are here to this webinar in topic of astrophysics, the role of plasmas discussion today. Firstly, I want to extend my heartfelt thank to Dr. Janit 𝗬𝗓 for sharing the valuable knowledge and delivering the wonderful presentation today. And I would like to express my heartfelt thanks to our SEDS Sri Lankan team and the other participant university chapters and our Professor Rohan Senadira sir, and also all the participants for being a part of today's astrophysics journey. Finally, I need to express thanks to my SEDS OUSL team for being a part of today's webinar. Before we officially close, I would like to mention that we have some exciting events and resources coming up that keep it up on social media and join in us upcoming event. Yeah, thank you all and have a great night.
Thank you, Nipuni. We are now preparing to capture this moment with a photograph. So ladies and gentlemen, you will request to turn on your camera. Let's capture this moment together. Okay, thank you very much for your participation. Before we end, before we officially end the session, I'd like to mention that we have some exciting events and resources coming up that you want to miss. Be sure to keep an eye out for updates and invitation in your inbox. In closing, I want to thank you once again for your participation and wish you all the best in your future endeavors. Together, we are building a community and learning and growth. And I'm grateful to have had the opportunity to share this time with you. With that, we officially conclude today's webinar. Thank you. Have a nice weekend.